Last time, three-phase power came down to one clean formula, S equals √3 VL IL. But real systems run at several voltage levels at once. And adding up impedances across a transformer? The numbers turn into a mess. The fix is a tool called the per-unit system. Here's the network: a generator, a step-up transformer, a line, a step-down transformer, a motor. 3 voltage levels. And you want one number, the fault current when that line shorts. But those impedances sit on different sides of 2 transformers. To combine them, you'd drag each one across, multiplying by the turns ratio, squared, every crossing. It's a mistake waiting to happen. The per-unit system makes the transformers disappear. You scale everything to a common yardstick, and the messy ratios cancel themselves out. The idea is simple. You pick a base value for each quantity, then measure everything as a fraction of that base. It's like percent. 50% is just a value divided by its full-scale reference. Per unit is the same. One is per 100, the other per 1. You only get to choose 2. A base power for the whole system. Pick it once, and it's the same everywhere. And a base voltage, which you set in each zone, to match each transformer's ratio. Everything else follows. From those two, your base impedance is the base voltage squared, divided by the base power. Divide any real impedance by that, and you get its per-unit value. And here's the part that pays off. Let's work it out, with each part's math right under it. Here's the network: a generator, its step-up transformer, a line, and a fault at the end. The generator and transformer each carry a reactance from their nameplates, and the line is 50 ohms. First, the base: 100 MVA for power with zone voltages of 13.8 and 138 kV. Now, left to right. The generator's reactance is 0.2 per unit, but on its own 80 MVA, not our base. So we change it. 0.2 times 100 over 80 is 0.25. The transformer's 0.1 is already on 100 MVA, our base, so it simply stays 0.1. The line is in ohms, so first we need its zone's base impedance. 138 squared over 100, which is 190 ohms. Then 50 over 190 is 0.26. Now bring them together. In series, they simply add 0.25 plus 0.1 plus 0.26. 0.61 per unit. Now, the fault current. That's just Ohm's law. Voltage over impedance. Before the fault, the driving voltage is 1 per unit. So the fault current is 1 over 0.61, 1.64 per unit. For real amps, the base current on the line is 100 MVA over √3 times 138 kV, 420 amps. Multiply, and the fault is 1.64 times 420, about 690 amps. So, per unit, everything as a fraction of a base. Pick one base power and a base voltage per zone. Base impedance is voltage squared over power. Put each piece on the base, change base when the rating differs, divide ohms by the zone's base, and the transformers vanish. The network becomes one circuit you can simply add up. We took a real fault from 1.64 per unit down to about 690 amps. Next time, the transformer itself, built as a per-unit component. Subscribe, and I'll see you in the next one.